In the previous video lesson, I gave you an example of a person who walks 3 miles, stops, and then turns in another direction and walks another 4 miles. But what if we restrict ourselves to motion in only one dimension? So if the object can only move along an x-axis, then what if this person walked 3 miles and then another 4 miles, and they did so in a time of 1 hour? What would be their speed in comparison with their velocity? So from now on, if we write v with that little vector symbol on top of it, we know we're saying velocity and not speed. If I put the same symbol that we use for absolute value, if I put that in brackets, now I'm saying only the magnitude. And so this would be another symbol that we can use for speed, and this would be a symbol for velocity. So what's the difference between these in this example? Well, remember, the speed is the total distance traveled divided by the time. Well, the total distance is once again 7 miles, and the time is 1 hour. So we get a speed of 7 miles per hour, and we don't have to state a direction because speed's a scalar quantity. What about the velocity? The velocity is the displacement divided by time. But you see, when we constrict our motion to one dimension, to a straight line, to just movement along the x-axis, then the distance and the displacement are both going to be the same thing. So we get 7 miles in 1 hour, and we get 7 miles per hour. Now, I need to state a direction in this case. So let's make this person start out at the origin. So there's the y-axis. Typically, we say to the left is negative and to the right is positive. You don't really have to do it that way, but conventionally that's how it's typically done. So the way I can state the direction in this case is I don't have to say something like to the right, although that would work. I don't have to say east, although that would work as well if we think of the positive y-axis as being north and the negative y-axis as being south and so on. No. An easier way to say it would just be to call it positive 7 miles per hour. And so the positive implies movement toward the positive end of the x-axis. Now, if this same person were to walk 3 miles and then 4 miles, but in the other direction, three miles and 4 miles. Now their speed, once again, is 7 miles per hour, if it takes 1 hour to make this journey. Their velocity this time well, it would also be in magnitude 7 miles per hour, right? The magnitude of their velocity and their speed is the same when the motion is only in one dimension. But if I want to describe velocity, knowing that it's a vector quantity, I have to say to the left, or I have to say west. But an easier way would just be to call it negative 7 miles per hour. So going forward, well, bad choice of words. As we progress through the whole semester, we're going to use positive and negative, not so much as of a way of saying increase versus decrease. We're going to use positive and negative strictly as a way of describing a direction for vector quantities. Okay, so from now on, then, we really, as long as we're sticking to one-dimensional motion, speed and velocity are going to be very nearly synonymous. But I do want you to keep in mind the difference between vectors and scalars. So let's formally define velocity mathematically once and for all. Velocity, I'm going to leave off the vector notation because we're sticking to one dimension and realizing that speed and velocity are nearly the same thing. I'm going to leave off the vector symbol. Okay? We'll just say V average. So average velocity is distance or displacement divided by time, as long as we stick to one-dimensional motion. Technically, it should just be displacement and not distance. Distance over time is speed. Displacement over time is velocity. But either way, we're not going to use the word, we're going to use the symbol. So in symbols, average velocity is delta x over t, which is exactly the formula we've been using here, right? We've had a delta x of 7 miles in both of our examples, and so we're dividing delta x by time to get a speed of 7 miles per hour. Well, when a police officer pulls you over for going too fast on the highway and gives you a speeding ticket, he doesn't give you a speeding ticket based on your average velocity. That would be, if that were the case, all you'd have to do is tell the police officer, hey, listen, I plan on slowing down later, so everything on average is going to be fine, right? No, if you get a ticket for driving 80 miles per hour in a 50 mile per hour zone, it doesn't matter if you're going to go slower later and average things out. What matters is how fast you're moving at a particular instant in time. So we distinguish between these types of velocity. We talk often about average velocity, but then we also talk about instantaneous velocity. So we have v subscript avg for v average, and we have v subscript inst for v instantaneous. What if I were to put 3 lines in my equal sign? That's a way of saying equal to by definition. Okay, so I cannot derive this from any more fundamental formula. This is strictly what we mean when we talk about average velocity, right? This is how we're defining it. So in the same way, this is how we define instantaneous velocity. It's actually the same formula. It's delta x over t, but in a limiting case. As long as we limit ourselves to time intervals that approach 0, very, very small intervals of time, I guess this is the same thing as saying it's dx dt, right? So this should remind you of what you've learned in your calculus courses. So let's say, for example, I make a graph of the motion of an object. Now, this is not a north, south, east, west axis anymore. I'm making a graph of position along an x-axis versus time. So let me draw a supporting picture for this. So this is a person who's facing to the east, so they're going to move in the positive direction. There's the x-axis. They're starting out at the origin at x equals 0, and I'm just going to plot their movement over time. So we know they're starting out at x equals 0, and then let's say they travel to x equals 1 meter, x equals 2 meters, x equals 3 meters, and so on. And they do so at a steady rate. They keep the same pace for the first meter as they do the second meter. Then that graph is just going to look like some straight line. So if I want to find the average speed, let's say they travel 4 meters in a time of 2 seconds. 1 second, 2 seconds. 1, 2, 3, 4 meters. Well, you can see that if I divide a distance of 4 meters by a time of 2 seconds, I get 2 meters per second, which is nothing more than the slope of this line. But what if I didn't want to know what their average speed was for the whole journey? What if I want to know how fast they were traveling just right at this instant in time, right at t equals 1.5 seconds? Well, it turns out, because they were moving at a steady pace, their instantaneous velocity at that moment was also 2 meters per second. So what I've given you here is a trivial example, but let's imagine this same person moving, and it also takes 2 seconds, but they go very slow for the first meter, pick up their pace a little bit, and by the time they are covering the last one, so it's kind of the way a sprinter would come out of the blocks when he's running in a race. Then our graph of position versus time won't have this straight line appearance. It's going to start out with a very gradual slope, and the slope is getting steeper and steeper and steeper, and so maybe it's an upward trending curve. Now in this case, let's say they still covered the total distance in a time of 2 seconds, and the distance was still 4 meters. And so I say, what's the average velocity? Well, it's the same thing. They covered a total distance of 4 meters in a total time of 2 seconds, and we get 2 meters per second. But now I say, what was their speed right at the instant t equals 1.5 seconds? So if you think about it, this value of 2 meters per second is the slope of a line. It's like this. Their total distance can be represented by the height along this axis. So there we go. That's the delta x value. And then the time is measured across the horizontal axis. And so what I'm really doing by dividing 4 meters by 2 seconds is I've taken the slope of this secant line that goes from the origin to the final position of this runner. But you can see that the slope of this secant line isn't quite as steep as the slope of the tangent line at this moment in time. So that's probably the best way to think of instantaneous velocity. It's the slope of a tangent line on a graph of position versus time, whereas whereas average velocity is the slope of a secant line between any 2 points on a position versus time graph. Okay, so now we have a few different symbols, right? We've got that symbol, this symbol, that symbol, this one, starting to get a little confusing. So I guess strictly speaking, this would be a way of saying velocity, and we recognize that it's a vector quantity. This is a way of saying average velocity. This is a way of saying speed. So we're only interested in the magnitude. And then, of course, this is average velocity. And this is instantaneous velocity. So let me preview again some of the equations that we're building up to in this lecture series. Based on the definitions that I've given you so far, we're going to use those to work towards these equations that you've probably seen already. Delta x equals 1/2 v naught plus v times t. V equals v naught plus at. Delta x equals v naught t plus 1/2 at squared. And v squared equals v naught squared plus 2ax. Well, because we're sticking to motion only along one line, just movement along the x-axis, then there's no reason to distinguish between speed and velocity. So if you ask a question about all these equations, say, did the v in those equations mean velocity, or did they mean speed? For now, the answer to that question is simply yes, right? Did they represent speed or did they represent velocity? Yes, they same thing. All right. Now, do they represent instantaneous speed or average speed? They represent instantaneous speed. Okay, so without the subscript, this v means at the end of the object's journey, what was the speed at that given instant? And if there's a subscript 0, then I mean at the very beginning of the motion that we're studying, what was the speed at that very instant? So we're talking about instantaneous speed and velocity when we apply kinematics equations.